Did you know how logistic regression got its name? Did you also know logistic regression is the first good choice for particularly binary classification problems? Are you looking to understand logistic regression intuitively? If this is something that excites you, then you're at the right place. This is Manjunath for Data Science Galaxy. Welcome to my YouTube channel. Let's get started. I'm going to call out the agenda. I'm going to talk about several things today in an intuitive fashion for you to help understand logistic regression and along the way help bust some of the myths. Let me just call out the agenda first. So we're going to talk basically about logistic regression. I'm going to put it in a shorter fashion called LR, and we're going to talk about the introduction. I'm going to help you understand the setting where logistic regression is applicable. And we shall spend some time understanding the broad categories of logistic regression. Not logistic regression so much. We shall spend some time understanding the logistic regression categories, broad categories of algorithms based on nature of the dependent variable. And we'll spend some time understanding, after having introduced ourselves to logistic regression, we shall understand the mathematical representation of logistic function. We shall spend some time understanding the logistic function itself. We shall also spend significant amount of time understanding the ideas of odds and probabilities with an intuitive example, because sometimes people get confused with the fundamental idea of odds and probabilities. What is the connection? We see some intuitive examples. We shall also see this logistic function, or logit it is specifically called, how do we derive using odds ratio. Okay, we'll spend some time deriving the logistic regression. I'll simply call that as derivation. Then we shall see the idea of sigmoid function. What is this sigmoid function that you keep hearing in the context of logistic regression? And we shall spend some time looking at demoing the sigmoid function using Excel. In Excel, we shall see how do we look at this sigmoid function? What is the significance of this sigmoid function? I think this agenda is exciting enough for you to watch this video till the end. If you have not already subscribed to my channel, please subscribe and stay tuned for more. Without much ado, I think let's get going with the first slide that I've got for you, where I've called it dependent variable choice of algorithms. What I'm talking about basically here is, let me just bring up this content here. If you look at the nature of the data from the perspective of dependent variable, broadly you can think of them to be dependent variable can be continuous and dependent variable can be categorical. When I say continuous, you can think of this to be some numerical quantities. Let me write that so that you'll be crystal about what I'm talking. You can think of this to be some numerical quantities. When I say numerical quantities, I'm talking about, let us just say, profits, okay, sales or revenue. I'm talking about, let's just say, loss. I'm talking about cost. I'm also talking about, let us just say, height. I'll just abbreviate this, weight, etc. Basically the numeric quantities that I've got decimal point representation for the values. And the other part of the puzzle is dependent variable can be non-numeric, particularly categorical, and even more specifically discrete, like of the type 0 or 1, which typically we represent as, let us say, buyer or not. Okay, so mail is a spam or not. Let us just say, if you are dealing in healthcare, it can be malignant, cancer, or benign. Malignant or benign. If I have to give you a flavor of another dimension, let's just say finance, someone is a fraudster or not. Some transaction is legitimate or illegal transaction, things of that nature. Remember, the categorical does not have to be limited to only the two levels. It could be more than two levels, We shall talk about what is the appropriate algorithm thereof little later in the journey. So suffice it to say, I've given umpteen number of examples for you to be able to appreciate. Dependent variable could be typically continuous and therefore of the type that is numerical quantity of profit, sales, loss, and can be non-numeric or nominal. It could be having two levels, like in the case of buyer and non-buyer for a categorical dependent variable, or it could be more than two levels for categorical dependent variable. Like for example, you can think more than two levels could be, I'll just abbreviate this, high risk, medium risk, and let's just say low risk. Or if you look at any product adoption cycle, it could be more than three categories also. Okay, if you look at, for example, for that matter, performance appraisal, then you can categorize people into more than 4 or 5 categories of performance. So these are some examples. In all such cases where a dependent variable is continuous in nature, we typically look at regression algorithms. It could be of the type, academically speaking, simple linear regression, or more specifically, we could use multiple linear regression and smart variants of regression for predicting numerical outcomes. On the other side, for the problems that you're dealing with in the real world setting of the type, which requires certain categorization or classification, you use popular algorithms that are classification oriented. And I'm looking at positioning logistic regression today as a classification algorithm. And I mentioned at the beginning, there are some myths floating around in the world in the form of misinformation. So I'm just going to touch upon that in a bit. Allow me to say, I'm using logistic regression also for classification setting. Hope that is crystal with everybody. I think this is good enough for this slide. Allow me to move on. So let's just deep dive into the world of logistic regression. First thing is to say, logistic regression gets its name from logistic function. So I'm going to put that. It gets its name from logistic function. I'm writing it so that you will also be following in a systematic fashion with me. Another thing is to say, logistic regression, if you look at, they belong to a class of models called generalized linear models. For short, we can write it as GLM. Logistic regression uses the idea of Logit function or logistic function, and therefore they belong to a family of models called maximum entropy classifier. I'll write this. Some of you may not be familiar with these things. Maximum entropy classifier. Pardon my writing. I'm writing it in capital letters so that you'll be able to appreciate what I'm writing. Okay. Basically, logistic regression is a supervised learning technique. You know what? Let us bust the myth. It is high time we did that. I'm all for not spreading misinformation. If we do not know something, fair enough, we will admit and we'll learn together, but we should not spread misinformation. A lot of people refer to logistic regression as a classification technique and not a regression technique. That's far from the truth. Logistic regression is a regression technique as a supervised learning technique applied for a classification setting. Let me repeat, because that merits that kind of repetition and emphasis. Logistic regression is a regression technique applied to a classification setting. Having said that, I talked in the previous slide, if you recollect, for regression, multiple linear regression, you can think of logistic regression as an extension of multiple linear regression applied to a particular situation where your dependent variable y is discrete in nature instead of continuous, as in the case of MLR or multiple linear regression. Okay, I don't want to confuse you. You can think of logistic regression to be an extension of multiple linear regression for a particular situation where your dependent variable is categorical in nature. Okay, so I already mentioned multiple things about the logistic regression. Moving on, I called it out explicitly. I've already talked about it. Is a regression technique. The operating word is this. Is a regression technique applied to a classification setting. Make no mistake about it. It's very, very important to understand this. What does it do? As a supervised learning technique, applied specifically for classification. You know what? Specifically, logistic regression, if you look at, like I already mentioned in the introduction, is a good first choice for binary classification problems over other complicated methods. In fact, it is a good first method for not just the binary classification, it's a good first method for modeling probabilities. Think about this for a moment. Probabilities values can range from 0 to 1. So it is the interval of 0 to 1. Logistic regression could help you directly predict the values which are restricted to the values 0 and 1, as in that of probabilities. That's why it's a natural first choice for modeling probabilities. In fact, mathematically, if we examine this, I'll talk more about it a little later. Logistic regression is attempting to estimate the conditional probability of the event. It in fact is attempting to estimate the conditional probability of an event. Conditional, I'll just be cryptic here for writing probability, but you get a sense of what I'm talking about, probability of an event. Okay? When you look at closely, particularly the logistic regression models are estimating how probability of an event may be affected in a supervised setting given that there are one or more independent variables. You get a sense what we are talking about? Logistic regression? Let me just paraphrase it properly to convey a gist of what I'm trying to convey. Logistic regression gets its name from the logistic function. It is a supervised learning technique, otherwise a regression technique applied for classification. It's a good first choice for binary classification and a great first method for modeling probabilities. When I say modeling probabilities, mathematically, if we examine logistic regression, it is attempting to simply estimate the conditional probability of an event from happening. Therefore, the logistic regression models are trying to estimate how probability of an event could be affected given one or more independent variables in a supervised setting. Hope that is very clear to everybody. Another point to understand from the perspective of logistic regression is the coefficients of logistic regression are typically used for advice, as they help you to quantify the relationship between the outcomes and the input variables that is going into the logistic regression model. So the last point, though I've listed as the last, it is by far highly impacting statement to talk about. That's because logistic regression is a white box model. That is to say, I'm not just able to come up with a mathematical representation, I'll also be able to explain and interpret the model reasonably well. And therefore, I would use the logistic regression coefficients for advising my clients, because this helps me to quantify the relationship between my outcome of interest or phenomenon of interest and the inputs of the model. Like for example, if we know the salary of a person, let us say the disposable income of a person, credit score of a person, experience, etc., if I'm able to come up and predict who is likely to default on the loan payment or otherwise, then I can establish a relationship between the outcome of interest, that is defaulting or not, with the set of input models to go ahead and advise my clients as to who should be loan approved for and who loan should not be approved of. So there are certain real world implications of translating the coefficients into advice for your clients. Okay, and the quality of the advice would be enhanced when you do not have, let us say, the correlated variables in the logistic regression setting. It is another matter. Logistic regression is fairly robust for multi-collinearity or the collinearity issues, but it's worthwhile to remember the advice could suffer the quality, I mean, when I say advice, in presence of the multi-collinearity. I think that's pretty much I wanted to cover in terms of what we wanted to talk about the logistic regression. Moving on, in the previous slide, we looked at the broad categories of the techniques itself based on the nature of the data. Now I think it's time to switch gears to look at the variants of a logistic regression itself. If you look at this slide, I think it's a neat and tidy. I've just called it logistic regression broad categories. If you look at this slide, you can think of logistic regression broadly. It could be divided into two categories in terms of the algorithms. One is what is called the binary logistic regression. This is of the type defaulter or not. Just I'm writing it one more time for better clarity here. So one can be categorized as binary logistic regression, where you will have strictly the dependent variable that is binary here. Okay, so we're talking about dependent variable when it is binary and calling it as binary logistic regression. In fact, the logistic regression of the flavor that I'm discussing in this video is that of binary logistic regression, to be even more precise. Another thing, depending on the number of levels, I mentioned, just to give you an example of a risk profile, high risk, medium risk, low risk. If you look at, these are more than 2 levels for the dependent variables. And therefore, you can think of applying something called multi-nomial logistic regression. So broadly, depending on the levels of the dependent variable, logistic regression can be classified into binary if the dependent variable is strictly binary, and if the dependent variable will have more than, let's say, 2 levels. It could be any number of levels, but it is usually it would be finite number of levels. More than 2 levels, whenever you have for a dependent variable, you're talking about a setting where you're applying multiple nomial regression for classification problems. In either case, you could deal with either a binary or a multi-nomial classification setting. Okay, so going forward, if you notice, I've not written anything under binary because I've said enough. Under multi-nomial logistic regression, if you think about it, I could further go about splitting it into 2 subcategories, if you will. One is called ordered multi-nomial logistic regression, where it has to do again with the dependent variable, but the dependent variable will have ordered values. Dependent variable will have ordered values. Okay, this is an important distinction further to look at. When the dependent variable has ordered values, you would look at applying specifically ordered multi-nomial logistic regression. When your dependent variable has unordered values or categories, unordered values or categories, particularly then you will apply what is called nominal multi-nomial logistic regression. I think everybody should be crystal about that. If you remember, I've been repeatedly saying logistic regression gets its name from logistic function. Okay, by now you would have guessed what I'm going to do in the next slide probably. I'm going to talk about the mathematical representation of logistic function. Okay, so we're interested in probability of an event happening, and usually we represent it as y is equal to 1 for success. Probability of an event happening can be represented as 1 upon 1 plus e to the power of minus beta dash x, where your beta x is similar to your multiple linear regression representation. So this is a mathematical representation of a logistic function. This is the representation also of a sigmoid function. When I say sigmoid function, we're talking about a S-shaped curve like this. I'm going to spend more time explaining what is this and implement this in an Excel for demo so that you will be crystal about what I'm talking about when we talk about logistic regression. Okay, for now, let's just understand probability can be represented as 1 upon 1 plus e to the power of minus beta dash x, where beta dash x is simply a representation similar to multiple linear regression. The exponentiation form here, it makes it little complex in terms of the computational power and things of that nature, but I shall simplify. In fact, in little later in the journey, I shall go ahead and use the idea of odds to actually come up and derive this to show how we can go from odds ratio to calculating the probabilities. That's the crux of logistic regression if you look at. Okay, so I think I'm going to leave this for now at this point. As promised in the beginning, I'm going to talk a little more about odds and probabilities. Let us call this slide definition, or this, not the definition, sorry. The title of this slides to be odds and probabilities. If you want to understand logistic regression in an intuitive fashion, needless to say, you should have a good grasp of the understanding of odds and probabilities. I reckon many of you would be very familiar with the idea of odds, okay? And therefore, idea of probabilities you would be more comfortable. And I want you to be comfortable with the idea of odds. It's easy peasy in terms of understanding. I shall simplify further like I always do for an intuitive understanding by giving some examples. Let us just first think about probabilities. You all know probabilities can be between 0 and 1. It cannot be negative and it cannot be greater than 1 while being positive. It has to be strictly between 0 and 1. That's why we're using the idea of logistic regression for modeling the probabilities. Anyways, if you look at, okay. So if you look at probability, I can represent probability as a function of odds. So I could represent probability as odds divided by odds plus 1. I'll simplify this. Bear me out on this one with a little bit of a theory. We shall take a concrete example to internalize this much better. I promise you that. Probability can be thought of as odds divided by odds plus 1. Okay. So if I can simplify this, I can represent odds as probability of success to the probability of failure that can be represented as P upon 1 minus P. So I'm going to call it out. This is probability of success. 1 minus P, we can think of this as probability of failure. Whereas odds is probability of success to probability of failure, ratio of probability of success to probability of failure. You could represent probability using odds as probability is equal to odds by odds plus 1. Something interesting to note here, I already alluded to at the beginning of this slide. So probabilities can be strictly between 0 and 1. Worth noting that odds can be greater than 1. It's important distinction. While probabilities cannot be greater than 1, odds can be greater than 1. So I think it's worthwhile to understand this with a concrete example so that you will get a essence of what I'm talking. Here is a popular example that I give people when I'm talking about odds and probabilities. Sorry for the overlap there. Let us just say you have gone about 3 attempts for a fishing expedition. I don't know, some of you may be interested in fishing expedition. You may be looking at a fishing expedition, and let's just say I've taken the odd number of attempts for a reason. Fishing expedition, just to make sure. Remember friends, this is to internalize the idea of odds and probabilities. You have gone about making 3 attempts for a fishing expedition, and let us say what constitutes success is 2 attempts that you have made. Out of 3 attempts, you were successful in catching the fish in that expedition. And let us just say you have failed only once. 1 attempt you have failed. Okay, let me clarify this. You have gone about a fishing expedition on a certain day and made 3 attempts to catch the fish. In 2 of the attempts you are successful, and in a lonely attempt you have failed to catch the fish. So what do you think is the probability? I think that's the easiest thing. Probability is nothing but the success outcomes divided by the total number of outcomes. Total number of outcomes is 3, out of which the success outcomes are 2. So it is 2 upon 3. This is your probability, isn't it? That is very, very simple to understand. Probability of an event is success outcomes divided by the total number of events. That is 2 by 3. So now let us define odds. Odds can be thought of as, if I go back to the previous slide, let's just go back, because I think it's sometimes important to toggle between these slides for you to be able to understand this better. So odds is P upon 1 minus P, where P is probability of success, 1 upon P is probability of failure. So I'm going to plug the values into this using the idea of odds now, nothing else. Okay, let us select the pen. So P upon 1 minus P. Okay, that means probability of success. Probability of success is 2 upon 3. So can I write this? Probability of success is 2 upon 3 and probability of failure is 1 upon 3. Is everybody okay? I think 3 and 3 gets cancelled. So I can write odds as 2:1. So we mention it as 2:1. Otherwise, it's called the odds ratio for a reason. So I recommend in this case 2 by 1 is equal to 2. Don't simplify. If you have the numerator and denominator as a ratio, it will be easy to interpret. So it is a 2:1 odds. You must have heard this term in other walks of life, particularly in sports, in betting industry, they talk a lot about odds. Okay, so hopefully with this concrete example, you'll be a little more crystal about what is the idea of odds and what is the idea of probabilities. Okay, and the connection between odds and probabilities. I think we have covered pretty much of the ground. Something more to add here is therefore to look at the sigmoid function, the derivation of sigmoid function. Remember, we started off by saying sigmoid function, I'll just go and put it here, is nothing but p is equal to 1 by 1 upon e to the power of minus beta dash x. If I can think of like this as my sigmoid function, how do we derive? I mentioned that we can do a simplistic derivation using logarithm. Okay, so what I'm going to do is, so I can take like this p upon 1 minus p, which is nothing but the odds ratio. So I'll call this as odds ratio. I can represent it as p upon 1 minus p. I can, where p is probability of success, 1 minus p is probability of failure, I can equate this to the sum term on right hand side, where you can think of beta to be a vector, and beta dash x is nothing but beta naught plus beta 1 x1 plus beta 2 x2 etc. beta k xk. You can think of it like that. Okay, so what I've done, I've taken odds ratio, that is probability of success to probability of failure, and equated them to that to some term beta x, where beta is a vector and beta x represents some mathematical form like this: beta naught plus beta 1 x1 plus beta 2 x2 etc. beta k xk. But I have to go from odds ratio to probabilities. So I'll think logically how to get there. So one of the ways of doing it is taking a logarithm. Logarithm of p upon 1 minus p can be equated to beta x on the right hand side. I've simply taken a logarithm. Okay, so if you look at this portion, log of p by 1 minus p is called a Logit function or a logistic function, and hence the name logistic regression. By now, I think you're able to relate the two. So what I want to do from here onwards is to go to probabilities. I've got log of odds. So I can think of this to be log odds. Okay, this is the odds ratio, this is log odds. So how do we get rid of, mathematically speaking, logarithm in a mathematical form is to exponentiate. That's because exponentiation and logarithm are opposite of one another. If I can exponentiate this, then I can get rid of the logarithm. So if I exponentiate on both the sides, then what remains on the left hand side would be p upon 1 minus p. Because I've exponentiated, I can represent the exponentiation with the English letter E, exponentiation of beta x. Hope everybody is clear on this. I've taken, think of this to be anti-logarithm, or think of this to be something opposite of logarithm, and therefore the exponentiation. I've gotten rid of the logarithm, and therefore I have to use the exponentiation as the mathematical idea. So on the left hand side, I shall remain with p upon 1 minus p equal to exponentiation of beta x. Because I want p eventually, so I'm going to do a cross multiplication retaining p on the left hand side. So what I'll do is e to the power of beta x multiplied by 1 minus p. So simple cross multiplication while retaining p here. So I'll do some adjustments here. What I'm going to do, I'm going to say p is equal to e to the power of beta x into 1 is e to the power of beta x minus p times e to the power of beta x. Further simplification, I shall write here on the space that's available on this side. What I'm going to do is minus p to the power of, minus p into e to the power of beta x. I shall bring it to the left hand side. So what will happen then would be p plus p times e to the power of beta x is equal to e to the power of beta x. Hope from the other side when you're watching on this video it will be legible. So I'm going to take p as the common factor. P times 1 plus e to the power of beta x is equal to e to the power of beta x. What I'll do is I want to retain p here, or divide both left hand side and right hand side by this term called 1 plus e to the power of beta x. So I shall have only p on the left hand side. On the right hand side, I'll already have e to the power of beta x. So I shall divide this by e to the power of beta x. If you wish, you can retrain at this level of detailing, which is same as this, which is same as exactly same as this. Only difference is if you divide the numerator and denominator by e to power of beta x, e to power of beta x by e to power of beta x makes the numerator 1, and on the denominator e to power of beta x by e to power of beta x makes it 1, and on the left of this plus symbol 1 upon beta x can be represented as e to power of minus beta x. If you simplify the numerator, if you divide the numerator and denominator by e to power of beta x for further simplification, you will be left with this simplest form of representation, where from the odds ratio you are going to look at the probabilities. That's why in the world of logistic regression, to understand the probabilities, we use the idea of odds. Okay, I think with this I have come to whatever I wanted to cover in this slide, and I'm going to take this guy here, p is equal to 1 upon 1 plus e to power of minus beta x, and show you how is this going to give you a sigmoid function. A simple word of a caution on the sigmoid function, not so much of a caution, I probably said it in a jest. What I meant was, you want to understand the idea of sigmoid function. So I'm going to write on the left hand side the mathematical representation one more time, and I shall show you p is equal to 1 by 1 upon e to the power of minus beta dash x. This is your sigmoid function. How does this look like when you look at in the context of logistic regression? Is the S-shaped curve that I alluded to. It will not exactly look like this. It will look something very similar to S-shaped curve. It is a profound application even in the financial domain and various other domains, and we shall use even in the world of logistic regression. In fact, if you look at, I said logistic regression is estimating the probabilities and modeling the probabilities to ensure strictly between the interval 0 and 1. The sigmoid function is what is enforcing the probabilities to be between 0 and 1. In fact, to be even more precise, we first model the probabilities using logistic regression. We bring in the idea of the threshold for classification. That's why it becomes an application for classification setting. Otherwise, it's regression predicting model probabilities of an event. And using the idea of threshold, we convert them into classification. Okay, so what I'm going to do now, I'll switch gears to Excel file and then show you how do we go about doing this. I think it's important that you understand at that level of detailing as to how does this logistic regression would look like in Excel. How do we actually calculate the formula? How does it actually go about depicting the sigmoid curve? I think I have to go ahead and increase this view or zoom it a bit for better clarity. I shall simply call it as, let us say, beta x on the first column, and here let us call this as we have been beating this to pulp, Logit. So allow me to do some small creation of the data. I'm going to take from minus 10, minus 9, let us say minus 9 to plus 10. Okay, so I'm going to select these two and I shall drag it and see if I can go up to plus 9. Yeah, so I've got the values. Let us just put this into align it center. Okay, so let me zoom it a bit. So I've taken this as values of beta x to be minus 10 to plus 9, and with the idea of looking at this formula for submission, for submitting those values. Which one I look at? I prefer to look at, let's say, instead of further simplified version that I've been talking about, I'll use this. What I'm going to do is calculate the probabilities using exponentiation of beta x divided by 1 plus exponentiation of beta x. So I'm going to use this expression for calculation using the formula in Excel. So how can you use? You can always use an equal to sign to invoke a function inherently in Excel, built-in functions, mathematical functions. For example, exp would give you the exponentiation invoking of the function. So I'm going to say exponentiation of beta 2 divided by 1 plus exponentiation of beta 2. Sorry, beta x. I've been saying it as beta 2. My apologies. I'm going to say, okay, I'll just keep the cell here. Focus here so that you'll see this. This is exactly similar to, friends, exponentiation beta x divided by 1 plus exponentiation of beta x. Okay, I've simply calculated using an equal to sign and invoking a built-in exponential function. So if it is working fine, I'm going to shamelessly drag and drop to get some values of probability here. Okay, so if it's not working fine, then I've done something wrong here. If it is working fine, then I've got something right here. Okay, so let us just see. Values look to be incorrect because probability values cannot be greater than 1. I must have done some mistake. Let me just rectify it. Let us just see this. Exponentiation of A2 is what I meant. I can see here. Give me a second. Let us just delete this. Okay. Exponentiation of A2. Oh, can you see it, friends? I have just made a mistake here by mentioning, instead of A2, I mentioned A3. Probably that's a mistake. So these human errors would happen. I think we got it right now. Okay, I think we got it right. See what happens if I plot this in a plot. Okay, let's just see and look at recommendations from Excel, and I prefer to look at this chart. Can you see? Voila, this, my friends, is the idea of sigmoid function. Okay, so what I'm going to do this, okay, give me a second. If I don't have much space here, I'm going to insert a new slide here and do Command A, delete all of it, come back and shamelessly copy this guy, because I can go ahead and write few things on that. I could have done it there, but I put it into this slide for better clarity so that I shall explain all of the intended ideas in slide view mode here. So let's go here and take a pen, and here you go. This is S-shaped curve. Can you see this? S-shaped curve. This, friends, is the sigmoid function. Okay, so if you look at it, these are the probabilities. See here, it is gone maximum up to 1 and minimum of 0. And these are all the positive probabilities of an event happening given the attributes of the information in the independent variables. Let us say I'm interested in a classification problem of classifying a loan borrower into defaulter or not. So what I'm going to do is to bring in a threshold. I'll talk that in a bit, but allow me to explain a few things. Notice here, many values here are closer to 0. You can think of this as, let us say, if the salary is less, the probability of someone buying a own home is less, or a own house is less. As the salaries increase, the probability increases, and you will have certain values here. And there could be somebody whose salary is less but would have bought a home. There could be somebody whose salary is high wouldn't have bought a home. So those are called misclassification. So to classify somebody, what I'm going to do, let's stick with, for example, better example like defaulter. Let us just say probability of default calculated by the estimation of the logistic regression is 0.6. Okay, I'm going to put a cutoff here at 0.5. Okay, this is my cutoff. How do you actually optimize a cutoff is completely a different discussion. So 0.5 is my threshold. So I'm going to compare probability of this borrower with that of my cutoff. So this borrower probability of default is greater than my cutoff, and therefore I classify this borrower as a defaulter. Usually we call that as a success. We represent that as 1. If some other person's probability is 0.4, which is less than 0.5, we can classify that person to be a non-defaulter, usually represented by 1. So what we have done, we have taken the continuous values of probability or the modeling probabilities, introduced the idea of 0.5 as the threshold to classify into defaulter or not. This is where logistic regression is a regression technique applied to a classification setting. Worth noting, there are several metrics associated with it, including precision, recall, confusion matrix, many things, concordance, discordance ratio. There are a lot more. Probably I can do a whole video dedicated to that. If you wish, please let me know in the comments. Okay. Worth noting here, many of the metrics for performance evaluation of such logistic regression model, or for that matter, any model to be even more generic, depends on this threshold. Why? 0.6 being 0.6 for that borrower. If I increase the threshold to, let us just say for whatever reasons, I'm going to increase the threshold to 0.7. Now 0.7 is greater than 0.6. That means you will have the line somewhere here. I'll put it as a dashed line or a perforated line. 0.6 is below this. So you would still classify this to be a non-defaulter. I'll represent it as 0. The probability of default remains the same, but the threshold makes the interpretation completely different. Here is an intuitive example that I give to people for better understanding. It is like you take an exam where the cutoff mark for a pass mark is 35%, 35 out of 100 is the pass mark. You will have a lot more people passing the exam. If I increase it to 65%, less number of people would pass the exam. If I'm crazy enough to increase it to 90%, even lesser number of people. But I get a sense of, depending on what I give the threshold or the cutoff for pass marks, accordingly my interpretation of the classification would be. So metrics for classification is heavily dependent on the threshold that we use. I think this video is getting longer. I'm going to stop here by summarizing. Logistic regression by far is a go-to technique for modeling the probabilities and applied for a classification setting. Even more importantly, we busted the myth that logistic regression is not a regression. Don't get misled by misinformation floating around in the public domain. So you need to understand and make sure logistic regression is a regression technique applied for a classification setting. Particularly, we apply it as a classification setting with the idea of threshold coming into play. Otherwise, it's simply a regression of sorts. If you look at just modeling probabilities, probabilities can be continuous. So therefore, it is a regression technique. Notwithstanding that, I've given you or introduced you, for those of you who are brand new to this world, to very basic, simplistic version of a binary logistic regression. But the ideas can be taken forward to smart variants called multi-nomial logistic regression. But the ideas at its core would remain the same. What would change is the number of levels. I want you to tell me, is classification problems tough when you have binary classification, or it gets tougher when you have multi-nomial classification? What do you think? I want you to answer that in the comment. And if this video, if you think this was useful, please give it a like. If you have not subscribed already, please subscribe and stay tuned for more. Share it with your community and friends for better reach, for maximizing the information and leveraging the information. And hopefully you have made it this far for us to be learning this together. This is Manjunath thanking you and signing off with the promise that I shall talk to you in my next video with even more insightful and meaningful and valuable information. For those of you who have tuned into my channel first time or are coming back in the new year, Happy New Year to every one of you. So wish you well, happy learning, happy modeling. I'll talk to you in my next video. Take care. Bye-bye.